Check out what came in the mail today. Finally, because this item comes all the way from Russia. Check it out. Look at those stamps. Par avion recommande. That doesn't sound very Russian, does it? But check out those stamps. Russia, 2009. It's kind of an old stamp. A whole bunch of them on there. Look at that. Russia. There's something you don't see every day. Well, unless you live in Russia, then, well, yeah, you do see it every day. And I gave it away. You know what's in there. Tubes, 6 pieces. Well, you've already seen the title of the YouTube video probably, so you can guess what's inside here. Anyway, the reason I say finally, this finally arrived, is because, well, you know, I've been waiting for this for early January, so 3 months or so, give or take. I actually ordered it on eBay from Russia, and they came all the way here to the United States, went to my house, and I had just moved. I didn't anticipate the move. It happened somewhat suddenly. I didn't move far away, but yeah, unfortunately, even though you do a change of address with the USPS, that is not enough to get it forwarded to your new address. I thought it would be. I was wrong. What happens? Well, I called USPS, I filed all the paperwork, and it went all the way back to Russia anyway. Fortunately, the seller for this, great seller, I might leak in the name, I might not bother, but they were a great seller, easy to work with, and they were willing to resend these tubes to me all the way back from Russia to, 5 miles away from where they had been originally, for free. So that was great of them. Now, my only concern is these are tubes, and, well, yeah, they're just kind of in an envelope. I can feel some foam in there, but, man, from Moscow to Detroit, and then back to Moscow and back to Detroit, yeah, I don't know. I guess we're about to find out. Okay, well, I got my knife, and let's get this thing open. See what it looks like. Be careful here. This is actually a really dull knife. It's kind of dangerous. Grandfather always said a dull knife is more dangerous than a sharp knife. I think he's right. Okay, anything else in there? Nope. Okay. Oh, need my knife again. Let's see how these things fared on their long journey. I mean, it seems to be packaged fairly well. I guess it could be better. Could be worse also. The way some people pack things on eBay. Hopefully the tubes are all insulated from each other at least, and they weren't clanging around. Move that away. Oh, wow. Okay. Well, I guess they did pack it pretty well. A few more layers here. I was worried by the envelope, because it could easily get crushed, but I guess envelopes, they're not just throwing them on top of each other. Maybe they are, I don't know. Oh, look at that. Yes, these were well packed. Alright, let me get the rest of these open and I'll show you what we've got. So what was in the package? Well, you've guessed it by now. Real, bona fide, IN14 Russian Nixie tubes. If you're not familiar with Nixie tubes, well, what they are, and you might be able to see, if I can zoom in, hopefully it won't go blurry on me here, you can see the numbers in there, kind of stacked on top of each other. You can see a 7, 6, maybe you can see an 8 there. What it is, in the days before we got spoiled with our TFT displays and our LCD displays, or even back before 7-segment LED displays, you actually had to create numbers using vacuum tubes. So if you wanted to do something that wasn't analog, at the time everything was an analog meter, where you literally just have a meter swinging like that. That was all you had on a scale. So if you wanted to have something that was digital, where you actually had digits like this, you needed vacuum tubes, Nixie tubes. So what is a Nixie tube really? Well, what it is you have these numbers you can see stacked on top of each other. Let's see if we can see it from the side. No, not really. But all the numbers are just stacked on top of each other, 0 through 9. And you can see that kind of mesh in there. That's the anode. Each number is a cathode. So you've got those 10 cathodes in there and one anode. And these tubes are actually filled with gas. They're filled with a mix of neon gas. There's some mercury in there and some other gas I can't think of off the top of my head. But essentially, when you run a high voltage DC current through it, about 170 volts I believe it is, this takes at only a couple milliamps, what will happen is the gas around the cathode, which is the numbers, will start to ionize. It'll glow, kind of an orange bluish glow, and you'll be able to see the numbers. So yeah, it's basically a diode. It's 10 several diodes in there. Kind of like, 7-segment LED display was 7 diodes, but yeah, this is vacuum tube diodes. I gotta love it though. It's just beautiful. The kind of effort that went into, sorry about that, to building these things, just amazing. I love it. You gotta love that. That's great. Anyhow, I figure what we can do, I'm going to test all of them, of course, but I figure let's hook one up and see if we can get it to work. Okay, so I got my hands on a data sheet for one of these IN14 tubes, or I guess backwards NH as the I and N is in Russia, I suppose. Anyway, I love this symbol here. CCCP, that's the Soviet Union symbol from back in the day when it was Soviet Russia. Yeah, gotta love it. These are, in fact, bona fide Russian tubes. So, yeah, it was translated. And I've got a description here. Gas discharge indicator is intended for visual indication of electrical signals in digital form in broad kind of equipment. A little bit of Rush English, I guess you would call it. I don't know. Anyway, so here's the schematic symbol for the tube on the left here. And admittedly, this does look rather complicated. You've got 13 pins there, which is a lot for a vacuum tube to begin with. But if you look at it in its simplest form, it's really not that complicated. It's actually just several diodes in one package, because you're only going to use one anode, and there only is one anode, the anode, and one of these cathodes at a time. So you've got several cathodes. You've got 1, 2 commas, and then you've got the numbers 0 through 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's basically a diode, a cathode and an anode. And then inside the tube you've got neon gas, and at some voltage that neon gas will start to ionize, and it will actually form a conductive path through the tube, just like a diode. If you reverse bias it, it won't work. You forward bias it, you get a conductive path. So that's essentially how it works. Pretty simple. Let me turn the page here, and we'll take a look at some of the data here. I know I actually printed this instead of screen capturing this time, because I needed to print it anyway for my own use. Anyway, basic electrical parameters. These are the really important ones, because here we have our 170 volt firing voltage. That's that ionizing voltage that I told you about. So when we work out these figures, that's the number that we're going to want to use, 170 volts on the plate, or the anode as it's called. And then the current for digits, because I'm not going to be using the commas. This is a clock, I have no real need for the commas, so I'm just interested in the digits. But 2.5 milliamps is the maximum current that we want to be running through that. So what we'll have to do is put a resistor on the plate of the tube to limit that current to a safe point. All right, and then the maximum allowable limit, safe power supply voltage for the tube, 200 volts. So that is the figure that we're going to use for our power supply. So here, our power supply, we want 200 volts, but for the anode, we want 170. That means we know how much we need to drop across that resistor to be safe. We got to drop that 30 volts. So that will factor into our information as well. And then there's information down here for multiplexing mode, where you turn only one on at a time, and then the human persistence of vision does the rest and makes it look like everything is turned on at the same time. And it says, you know, avoid soldering too close to the pins, and soldering and unsoldering. And after a long period of non-use, it's recommended to drain cathodes applying working current, for 1 minute for each cathode, which is what I'll do. I'll show you one of them here, but I'll go through each one, make sure all of them work, and also make sure that I train the cathodes, as it were. Alright, so as it turns out, getting the light where I want it has been exceedingly difficult. You can see I put my hand up, I still get shadows. Kind of have the light pointed at the ceiling now. I know there's a right way to do this, I just haven't figured it out yet. So anyhow, wanted to show you real quick how simple the schematic really can be for these Nixie tubes. So really, this is it. If you want to look at the very simplest version. What this is a drawing of a cold cathode tube, and that's what a Nixie tube is. It's a type of cold cathode tube, a tube that doesn't have any type of filament or heater. It's really, now it's almost a misnomer, because it does get hot as it operates. As the gas ionizes, it gets warm. But in reality, it's not a heated cathode, so that's where the term comes from. You know that it's a gas-filled tube when it has this up in the corner there. This dot indicates that there's gas in the tube. In this case, it's neon and some mercury and other things. And this indicates that it's a cold cathode. You know, your normal heated cathode, you'd have something like that. But in this instance, oh, that's nasty. Ugh, didn't know that was going to happen. Probably should have. Anyhow, ugh, gross. This indicates that it is a cold cathode type of tube. So cold cathode, gas filled. Anyway, now you can see this represents one of the digits, and that goes down to ground. And you have a current limiting resistor up there going to your B plus positive supply. And that's it. The current just runs down through the tube to ground. Very simple. And then it lights up. So, if you remember the values from our data sheet, the maximum allowable voltage that we can have on this tube is 200 volts. Alright? Because when this tube first starts out, instantaneously, before it has time to ionize and fire, this is going to be conducting no current whatsoever. And because it's a series circuit, if there's no current here, there's no current through the resistor. And what happens when there's no current through a resistor? There's no voltage drop. So the 200 volts that you see here, you also see here. So you don't want your supply voltage to be so high that you go above the absolute rating of the tube. So 200 voltage, absolute maximum for this. But I like that number, 200, so I'm going to stick with it. It's a nice round number. I could have went with, say, 180 volts and then dropped only 10 across the resistor. Somewhat, it's, you know, preference, but we'll go with that number. We also know that we want 170 volts here, because that is the maximum voltage that it takes in order to fire the tube, to get it to ionize. So we're going to use that number. When you're doing design like this, you have to use the numbers from the data sheet. It's the most accurate way. You're going to get the best results. Yeah, it varies based on manufacturer. It varies based on manufacturing tolerances. But these numbers are based off batches and batches of tubes. So to get the most common number, the average number, it's going to come off of the data sheet. If you have to adjust it later based on empirical evidence and data that you collect, you can, but the starting point for the design has to be based on that. And if I design a circuit board and I put the resistor in here, whatever we select, and it turns out it's not a good value, well, I can go and change it. As long as we get the power value right and we get the resistor big enough, we can always go and change the value later. Anyhow, I don't think we're going to have to do that. I think it's going to work just fine. But we've got our two voltages here. Now, we also happen to know that once this thing fires, conventional current flow there, it's going to act as a diode, and we're going to get current from RB plus down through the tube to ground. And we know from the data sheet that that is, or should be, limited to 2.5 milliamps. Presumably it'll draw more. If you were to just put the power supply directly across that, which isn't good, I wouldn't recommend it, your tube will work, but it's going to get really hot really quick. Eventually this is going to draw so much current that you overcome its wattage ratings and you're going to burn out the tube. So you want the protection resistor. We're going to limit it to that 2.5 milliamp signal that I recommended in the data sheet. So we've got 2.5 milliamps with a 30 volt difference. Now we can calculate that resistor. We'll call it R1. Why not? So that's going to be 200 minus 170 volts, which is the voltage drop across the resistor, divided by the current going through the resistor, and that equals 12 k ohms. So that becomes our 12 k ohm protection resistor. Alright, see? That was actually pretty simple. I told you it wasn't that complicated. Let's get this set up on the bench, and we'll go ahead and see how this thing works. Hopefully my tubes work. Fingers crossed. Let's go. Okay, so I've got my high voltage power supply here. It's my Heathkit IP17 power supply. It's good to about 400 volts, and you can see from our meter here that we're really close to our 200 volts, a little bit off, no big deal, 200.2 volts. So what I do, sorry, my bench is a little bit messy here, I've got some leads connected through the resistor there. I haven't connected it up yet, and ultimately to our Nixie tube, and I'll go ahead and turn off the power supply first for safety, but then hook everything up and we'll see what we got. Okay, so I've dimmed all the lights in the lab, and it's actually the afternoon right now, but I'm in my basement, so it's very dark. For some reason, something about having the lights off makes you feel like you need to whisper. I was only kidding. But yeah, it's afternoon and it's dark in here. Don't get much light in the basement, but wanted to be able to see this the best that we could. Anyhow, let me go ahead and flip the switch, and hopefully this thing will light up and work. It didn't. Why didn't it? Hello. What's going on here? Okay, I'm gonna try this again. Ah, there it is. Yep, what happened was I was not getting enough firing voltage in order to ionize the gas. I don't know if that's because I'm just now firing it up for the first time, or if this is going to be unreliable for me. But yeah, I love that. It's beautiful. It's actually kind of a false color. You're not seeing it exactly as I'm seeing it here. It's a little bit more toned down. It doesn't have as much glow as you're seeing, but this blue down in the middle there, you see that? That is actually there. That's from the mercury actually ionizing. The orange is the neon and the blue is the mercury, so it's just beautiful. I love that. You know, this is going to make one really nice looking clock. I'm getting excited already. Actually, once I turn the light on, it looks like we're getting a better representation of what I was seeing in the dark, so it's actually better with the lights. believe it or not. So yeah, you know, one funny thing about the Russian tubes, something that they did to save money, this may look a lot like an upside down tube, or rotated tube, I should say, and that's no coincidence because that's what it is. To save money, they actually, to make a 5, they turned a 2 upside down. So yeah, you know, save money. Why not? Well, I was not terribly happy with the results that I got when I turned this power supply on and the tube didn't light up. So what I'm going to do, I'm going to measure this resistor. See? 157.5. We got a little bit of a drop there in the power supply. It's not the most robust power supply, so there's probably some voltage drop there, but not the kind of drop we're seeing here. I'm seeing more drop than I would have expected. So, what I think I'm going to do, let's try, for instance, a 10K resistor and see if that works any better. Alright, I've got a 10K resistor in there now. By the way, sorry I didn't do the power calculation live. All you do is you take the current across the resistor, multiply it by that voltage drop. So we're talking, 2.5 milliamps times that 30 volt drop, which by the way is going to change now, but I haven't recalculated it. It'll be close enough to what the other power rating was. But that is important. We need to know what the power rating was. In this instance, it came out to be about 1/16 of a watt. I think it was something like 0.074 or 0.075 watts. So even a little 1/8 watt or 1/4 watt can easily handle it. I've got a 1/2 watt in there, so I know we'll definitely be okay. And I left that on for a while, and you know, it wasn't getting really hot. So no problems there at all. Let me fire this up, see what we get. It came right up that time. That's good. Let me go ahead and measure our voltages here. There's a supply, 198. 163. It's a little bit lower than I'd expect still. That's odd. Let's try another tube and see if we get any better luck. Let's go ahead and try this tube and see what goes on. Yep, that one came right up. Let's see what kind of a drop we've got here. There's our supply, and 157. One thing I didn't account for is that there's going to be some drop in that vacuum tube because, you know, it's not a perfect conductive element. So perhaps we're getting something like a 10 or 20 volt drop across that tube. And now that I think about it, that makes perfect sense. Although I think I'm going to stick with that 10K. Again, a nice round number. It's not a huge significant difference. It shouldn't affect the life of the tubes very much. And it seems to work much more reliably in getting these tubes to fire properly. Let me try another one and see if we get the same result. Try another one. Alright, well, I'm pretty well convinced. That came up as well. As you can see, there's an 8. I'm pretty well convinced that that 10K is a good value to go off of, so we'll work with that. Anyway, I hope you found this interesting. This is part 1 of what hopefully will be a series covering the build of an entire Nixie tube clock from beginning to end. I actually have some driver chips coming on the way, specifically designed back in the day. I guess back in the day would be the 1960s or so. Specifically for Nixie tubes. So I'm getting those from Russia as well, and we'll put those on the breadboard, see what they do. And that should be an interesting experiment to see how we drive these things. So we'll talk about that a little bit more when I get those. They haven't come yet. I'm actually going away on training for work for a week. So in that time, hopefully the new parts will arrive and I can do a video when I get back. So, you know, this will be a multi-part series. This is just part 1. They're not going to be contiguous. I'm actually probably going to do some other videos in between, but, you know, I'll try to keep them up the best that I can. Anyway, if you found that interesting, go ahead and like my video. Is it that way? That way? I think it's that way on YouTube. Hit the like button, because that helps out. Subscribe if you haven't done so already, and follow me on Twitter at OhmsAtHome. We'll see you. Oh yeah, one thing I wanted to point out, I don't know if you can see it, there's a little white standoff in there. That's how you actually delineate what pin 1 of this tube is, because from the bottom you can see there's 13 pins. There's no gap there, so it's not keyed. So you could actually turn this the wrong way and put it in the wrong way. And interestingly enough, I tried it just to see what would happen. If you connect one cathode to another cathode using one of the number cathodes as an anode, it will still operate. So make sure that you get the proper anode, and that's the one with the white standoff there.